Please work. Hello and welcome back to Calculus 1, section 4.3 on first and second derivative test. So what we have are the two tests which will help us analyze the function. We do not need to know what the function looks like. We just need its equation. And we can use these procedures to tell a lot of stuff about the function. Intervals on which function is increasing, decreasing, something that is called concavity, we'll talk about that. We will be able to sort out min and max points, learn about inflection points, and find out a lot about the function without its graph. So now, before we actually go into procedure and calculations, I'm going to draw just whatever function f of x, and I'm going to provide the x-axis because that is the only one that it's important at the time, right now. So now, I'm going to pick the max value over here, and I'll call that value x1. And I'm going to pick a minimum value over here. I'm going to call that x2. So those will be some values. We do have infinity and positive infinity on the x-axis. Now, I will also point out that here in, let's say, red, somewhere over here, there is going to be another value. Can call that value, how about x0? Whatever, doesn't matter. You good over there? Ah, shit.
He's just not coming back.
So, what do I have? First of all, I should write this in blood somewhere. Interval is a length on the axis between two values. Now I'll spell it out. So interval is a length on the x-axis between two values which may or may not include endpoints. So if I have A to B, that will be called open interval. That was a good effort. And if I have A to B with these brackets, that will be called closed interval. So the issue that we are having here is that the notation for open interval is the same as the notation for a point. And you have to distinguish between the two. It is not easy to differentiate if you just have something in writing, like let's say 3, 5, and then 3, 5. If I ask you, okay, which one is interval, which one is point, you can't tell me that, right? Because it's exactly the same. So from the context of the problem and from what you need to be able to distinguish between what's the interval and what's the point as we go along in this chapter. So what I want to show here is the increase and increase in the function. So if the function is increasing, meaning rising to the right, as you are moving to the right on x-axis, you will be walking up the function. So that's what it means for function to be increasing. And we see that the function in this case up there is increasing on negative infinity to x1 union x2 to infinity. So I have two intervals. These are two intervals here that cover the space. So now, what is that? That's all of this united with all of this. So in the interval, you have all x values whose y's are arranged in a increasing fashion. And then, in orange, I have a decrease, which is decrease. So f is decreasing, well, just decreasing from x1 to x2. So now I have these x values here all sit in the interval from x1 to x2, and the function above that interval is decreasing. And finally, we have this special red dot, which is the dot you guys haven't seen yet. That's the inflection point. I'm going to let's use green. So I'm going to highlight this part of the graph up to the point. And for this part of the graph, in green, I will say f of x is concave down, and that's from negative infinity to x0. So f of x is concave down. That will be the green part. And then let's pick another color. Light blue or light purple. Light purple. We have this part of the graph. And let's see if I can find light purple. Let's say this one. F of x is concave up from x0 to positive infinity. So I color coded everything. Maybe I should jump into blue and then highlight the increasing part, and then orange to highlight decrease. So all of the intervals, actually I did this poorly because this is much better. There we go. So you see the blue interval on x-axis. Those are the all x's for which the function is increasing. All of the orange, function is decreasing. All of the green, concave down. All of the purple, concave up. Concave up, very simple, holds the water. Concave down, spills the water. Increase goes up as you move to the right. decrease goes down as you move to the right. So these are the concepts, and all of this, including the critical points, min, max, and inflection, are going to be considered in this lecture as we do calculations. So we start our lecture with first derivative test. Now, first derivative test gives us intervals of increase and decrease, gives us critical points which turn into min and max, and that's that. There's lag. Now, what is the statement for the first derivative test? Call the first derivative test FDT, right? So abbreviate FDT. So here is the FDT statement. Number one, if f prime at some point at some point C is larger than 0 on interval AB, then f of x is increasing on AB. We already covered this, guys, when we did our 3.2 lecture. Now we are writing the formal stuff over here. 2. If f prime of at some point is less than 0, that's right, negative, on AB on some interval, then f of x is decreasing on AB. 3. If f prime of C is equal to 0, what then? Last class. Yes, it's constant, but what do we have? We have a critical point, which is min and max. Then f of x, because this is at the point C, it's not f of x, it's f of at C, so it's a single point. Then f of x has a critical point at x equals C. And then I'll put in a parenthesis here, min or max. So this is our first derivative test. And I'm going to run this statement against the function we all know, x squared. Very simple, right? We'll start with a very simple function. So f of x is equal to x squared, and let's just use the first derivative test to figure out all we can. Okay. Find the derivative, which is 2x, and then set it equal to 0 to find critical number. Now you can go and find the y value for that critical number, and you have your 0, 0 as a critical point. Put that aside. So now what we have here is we have a critical number. Here comes the procedure for the first derivative test. What you see here in black is last class, right? To find min and max, critical point. So what you see so far is what you know from yesterday. Now, what's the first derivative test? So for the first derivative test, we partition the entire domain. In this case, domain of x squared is all real numbers from negative infinity to positive infinity. We partition that at 0, which is our critical point. Then, in each of the regions, sometimes you have more critical points, you have more regions. In each of the regions, you pick a test point. And those are your C's to run in the calculation for the first derivative test. So what you do is you work on your f prime at -1. Well, the derivative, f prime, right, the derivative is 2x, so it's 2 times -1. And 2 times -1 is giving us -2. -2 is less than 0, which by our rule over here says that f of x is decreasing, so we'll draw the arrow to signify the decrease. Then we do the calculation for the other point at 1, so that's 2 times 1, which is 2, which is larger than 0, and that will give us the f of x is increasing because we have that the derivative is larger than 0, so that's going to go up. I hope that you see that we just got for free that 0, 0 is a minimum, because you see that the function is going down to 0 and then it's going up. So for free we learned that this point is a minimum. And that's the byproduct of doing the first derivative test, which is awesome. We don't have to mess with calculating extra points or knowing the graph in advance. We just take a look at the diagram we created. So the partitioning is you put down your x-axis, the domain you have, and then you partition it with every single critical number you have. We only had one, so we partition it there. And then, oh, by the way, if you have no critical numbers, then the whole thing is one partition, pick one number, any number, for a test point, and you're done. Now, the red numbers are test values. Those are the C's from the definition up there. And you plug those test numbers in f prime because it's the first derivative test. So you should be using first derivative to test the values. So test points go into the first derivative, and you calculate the value. If the value is negative, then it's less than 0, which means decrease. And then if the value is positive, larger than 0, is increase. Now, what is the type of the answer that you need to provide? So if you want those final 2 points, you have to say f of x is decreasing. You don't have to spell it out, say DEC, decreasing on, and you put negative infinity to 0. And the next line, f of x is increasing on 0 to infinity. So you are providing a summary, and that's your answer. This box is your answer. So you should be making sure that you have the conclusion. Now, we also found on a side that 0, 0 is a minimum, because the picture clearly shows function goes up, function goes down. I mean, we know what the x squared looks like, so we know it has a minimum and all these things, but it's nice to confirm on that particular function that this procedure worked. We'll do another 2 or 3 examples. Next example is my dear friend 1 over x. So when we find the derivative f prime of 1 over x, you get negative 1 over x squared. And if you set that equal to 0, you get negative 1 equal to 0. Well, that has no solution. If that has no solution, that means no crit points. We did this yesterday. And that further means no min max. So this is the procedure. If you have no critical points, in that case you will have no min and max. Now, to do the first derivative test, I said if you have no critical numbers, critical points, then partition is one partition. But then hold on. We have vertical asymptote here. So vertical asymptote is also something that partitions. So we're going to do another partition over here, add 0, from negative infinity to infinity. So I'll write, well, I'll summarize it later. Great. So now I have something to work with here. We have the vertical asymptote at 0 because the function is 1 over x. And then the derivative also has the vertical asymptote. Remember that the vertical asymptote location stays where it is as you take the derivative. So now I pick two test points. It's always the same story. And we do the first derivative test at negative 1. That's going to be negative 1 raised to negative 1 squared, which altogether is negative 1, which is less than 0, which means f of x is decreasing, so we'll put the arrow down. Now when you calculate the first derivative at 1, you have negative 1 over 1 squared, which is also negative 1, which is less than 0, and then f of x is also decreasing. So you have another decrease. We have no critical points, therefore no min and max values, and you see that there is a decrease on both partitions for this problem. So what's the answer? F of x is decreasing on negative infinity to 0, union 0 to infinity. It's decreasing on the entire domain. You can also specify on a side no min max. And if you want to consider this, just look at the graph. I'll erase this graph. I just want it here next to so you can see both things at the same time. So this is your 1 over x graph. We use the first derivative to calculate a whole bunch of stuff. But your graph for 1 over x, right, is the original 1 over x graph. So now, the black arrow here shows the decrease, and you'll see that this piece is a decreasing piece. As you walk to the right, it goes down. The other black line is also matching because this is also a decreasing piece. Do we all see that? So we use the first derivative to analyze the original function, and you see that it matches. We also had the vertical asymptote at 0. When you took the derivative, that vertical asymptote stayed at 0. And now we have these things.
See if there's an asymptote?
You are plugging those test points into the derivative, right? Because look at the notation, f prime of negative 1. So your test points, I'm going to put these test points in red. Right, these test points are x values which you placed into the first derivative. That's the title, first derivative test. So you are using first derivative to test these values so you can figure out decrease or increase. F of x equals e to the x. What's the derivative of e to the x? Also e to the x. Great. And when you set it equal to 0, what happens? No solution. Which immediately means no critical points, and that means no min max. So now what do? I take the partition. We know domain for e to the x is from negative infinity to positive infinity. Oops, I wanted to say just this. And do we have any critical numbers? No. Do we have any vertical asymptotes? No. So I'm gonna write here now in blood. No crit numbers and no vertical asymptotes equals the whole domain is one partition. So no critical numbers and no vertical asymptotes equals means the whole domain is one partition. You are free to pick any number under the sun because it's one partition and you will test that one number in the right. So which number should we pick? 1. Okay. Sure, why not? Here, 1. Is there an easier number to pick? 0 is easier, sure. But you already picked 1, so now you have to stick to it. So this is going to be e to the 1, which is e. E is larger than 0. So the derivative is larger than 0. That means that f of x is increasing. Since everything is one partition, it's increasing across the domain. And we know that because we know what the function looks like. So answer, f of x equals e to the x is increasing on negative infinity to positive infinity. No interruptions. We just go. Bueno? Okay. So it's time for us to take a look at 2 examples that are spicier from homework. They asked again, would you like any cookies? Of course. I accept cookies every single time. Never sent them. Sad. All right, looking for something cute. All right, just some basic stuff. How about problem 32? Looks cool enough. So for 32, they say f of x equals to square root of 2 times sine x minus x, and they want us to work on 0 to 2 pi interval. So that's 32. You have 3 cosine 3x, cosine squared x, then some stuff with the square root, so a whole bunch of cool problems you can enjoy. Where do we start? We start with the derivative equal to 0 to find critical numbers. We already know there are no vertical asymptotes because sine function and the linear function x do not have any vertical asymptotes. So the only partitioning will be done by critical numbers if we have any. So for critical numbers, we first have to find the derivative, which is square root of 2 cosine x minus 1, and we set this equal to 0. We have a trigonometric equation, probably the cheapest and easiest you can get, because you're now cosine x is equal to 1 over square root of 2, which is actually square root of 2 over 2. So when is cosine square root of 2 over 2? And we are on the 0 to 2 pi. So for your cosine, you have your pi over 4, great. And what else?
7 pi.
Yes. Seven pi, because cosine is symmetric on x-axis, so it will drop here. And so all students take calculus, right? C for cosine, and these all students take calculus, A, S, T, C, are all about where the positive numbers like root 2 over 2 would land. So cosine is positive in quadrants 1 and 4, which is why we have pi over 4 in the first quadrant and 7 pi over 4 to signify the fourth quadrant. Time to make the partition. So now we're going to f dt. Make the partition. Your domain starts with 0 and ends with 2 pi. So now your partition is finite. This is the first problem. We're not going from negative infinity to positive infinity. And the reason why is, well, look at the top line. They said they want to consider this function, but only on the interval 0 to 2 pi. That becomes your entire universe. Everything outside of that is completely irrelevant. So we have 0. You can go in the middle with the pi, in the middle with the pi over 2, and then in the middle of the pi over 4. Or you don't have to be that precise. You just need to know that there is pi over 4, and let's say 3 pi over 4, somewhere as these partitioning numbers. So now your job is to find which So you have your partitions, and now you need to figure out your test points.
Is that supposed to be 7 pi over 4?
That's what I said, 7 pi over 4. It's clearly 7 pi over 4. Look. See that?
I see.
That's a 7.
Yes.
All right, good. Thank you. So we have these 3 regions from 0 to 2 pi, and we can pick any values we want. Well, hopefully we'll pick pi in the middle, because that's cheap. And now you have to pick some less favorite values. What would be value smaller than pi over 4 that we can easily compute with trig functions?
Pi over 6.
Very good, pi over 6. And how about on the other end? Excellent. Not 7, sorry, 11. The full circle is going to be 12 pi over 6, because you have 2 pi, right? So if the end is 2 pi and you want to make that into denominator of 6, you have to multiply by 6 and 6, which is 12 pi over 6. So you have 12 pi over 6 at 2 pi to go 1 pi over 6 less to get the test, right? So that's how I got 11. Now I have to do first derivative test on all of these red values. And my first derivative was the square root of 2 times cosine of, in this case, pi over 6, and I believe it was minus 1, right? Yep. Good. What's cosine of pi over 6? Excellent. Minus 1, so this is root 6 over 2 minus 1. Do we need the number for this? The exact number down to 15th decimal? No. All I need to know if this is positive or negative. And if you can make that argument without calculating, awesome. If you have to use the calculator to figure out what the value is, well, you still have the number. You wasted more time, but you still have the value. So square root of 6 is more than 2. Square root of 6 is more than 2. I don't need to know how much, right? I just know that the square root of 4 is exactly 2. Then square root of 6 must be more than 2. When I divide a number that it's more than 2 by 2, I'll get a number bigger than 1. So this is definitely positive, without me calculating. Sure, go ahead, calculate. You will get 1 point blah, 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 and you will know it's bigger than 0. So the first part is increasing. Then we do the derivative test for pi. And that one is square root of 2 cosine pi minus 1. How much is cosine pi? Excellent. And then we subtract 1. So you have negative root 2 minus 1. You have a negative, and then you make it more negative. Great. I don't even have to calculate anything. I see I have a negative minus a number, so that's going to make it even more negative, so we're good there. And finally, 11 pi over 6, so root 2 cosine of 11 pi over 6. Well, that's going to give us the same value, same as pi over 6, because in the reference angle calculates the same way. in blue. What we got for free is x equals pi over 4 min or max? Max. And x equals 7 pi over 4 min. The way the arrows are arranged, you start at 0, going through pi, it goes up, hits the highest peak at the critical point, because critical points are either min or max. So hits the critical point at max, drops down, hits the minimum at 7 pi over 4, and then continues rising up. So answer, f of x is increasing on, and now the increase is the first and last. So 0 to pi over 4, union 7 pi over 6 and 2 pi. Yes, thank you. And f of x is decreasing on pi over 4 to 7 pi over 4. That is your answer. And you also have min and max values for free, right? Got it. Can you open the window? This little guy is gonna go out. All right. Oh, come on. Up, 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 up. Bye-bye. All right. First derivative test on one more example, or we can do second derivative, huh? Are we good with the first? Good? All right. Second part of the lecture is second derivative test. SDT what was there, gives us concavity and inflection points. So second derivative test gives us intervals, concavity and gives us inflection points. I'll put in parentheses to explain inflection points, change in concavity. So concave down changes to concave up changes to concave down. Your increase and decrease, they switch at min and max. Inflection points, change concavity. Change concavity. Now, before I go into the procedure for second derivative test, which is identical to the first derivative test, you just use the second derivative, all the steps are the same. and calculations. Before I go into it, let's understand concavity. Now, those of you who are in business and economics and so on, you're going to appreciate this. Everyone should, but I have to make everyone happy. So it's not only engineering here, right? Yeah, I know you. What I'm going to do is I'm going to propose 3 investment portfolios. All of these graphs are money versus time. Time can be months, years, whatever. They all start with the same investment of, let's say, 10K. And as the time goes on, there is a curve which shows the situation. My question to you is, ultimately, which one of these you would invest into? And why? Number 1, number 2, number 3. Well, I never said it's increased exponentially, but
It looks like it is.
it looks like it is. Aha. That's exactly what I want to hear. Faster rate of increase. Let me ask you a quick question. Looking at these 3 portfolios, which portfolio is making money? All of them. So which ones are increasing? All of them. But are they all increasing at the same rate? No, right? So this is why we're using second derivative to show concavity. You see, the one on top is concave down, and that's the worst one of all, because it starts picking up money quickly and then it kind of levels off and gets lazy. And some students are like that in the class. They start a really high note, and then by the end of the semester on exams 3 and final exams, just like, and then just, Other students start low, like the second graph, and then they get exponentially better, as you mentioned, right? Which is the best option for us to invest in. And then we have a constant rate of increase. So actually the third graph fits in between these 2 graphs on top in terms of the speed. So the first graph has a negative rate of increase. It's increasing, but it has a negative rate of increase. The third graph has a 0 increase, a rate of increase. And the middle graph is the one that actually has a positive rate of increase. If you have a positive rate of increase, that means that you are picking up, whether it's money or speed or whatever, you are picking it up ever faster, right? Every second that passes, you are collecting more. So if you were collecting $100 in the first hour, you're collecting $200 in the next hour, $300 in the next hour, $500, $1,000 on hour 5, right? That's the positive rate of increase. So it's not that, right? You are making money if you are. So this one over here is a study rate of increase. This is like receiving $100 every hour. Let's say you are tutoring calculus, right? It's not that you are tutoring calculus first hour for $100 and then the second hour for $120 and the third hour for $140. That would be this graph here. If you are tutoring calculus, then that's the constant rate of increase. Your wealth is increasing, but it's increasing at $100 every hour. So that's the third graph. Every hour you are receiving the same amount of money. What's the rate of increase for the first one? First, you get 100, Then next hour you get $90. The next hour you get $80. The next hour you get $70. Are you getting richer? Yes, you are still getting richer. With every single hour that it passes, you are getting richer than the previous hour. But it's not the same as if you go to this one and you say 100 for the first hour, 120 for the second, 140 for the third, and so on. Now you're looking at these numbers and say, yeah, right, that's, Tutoring calculus in New York is 120 an hour. So it costs you $30 to get there. Some of you are processing this information. Yeah. How much do you make a week? $400 a week? Yeah, it's 4 hours of tutoring in New York. A week. Anyway, so we'll go on. So this one over here, the sluggish one, will be known as concave down. This one will be known as concave up. And this one over here is the flat rate of increase, no concavity. Is the function increasing? Yes. Function is increasing. Great. But it's not concave because the rate of increase is constant. So how do we detect this? Concavity is detected by the second derivative test. And here is the statement. If the second derivative computed at the test point C is less than, or let's go with more than 0, on AB, some interval AB, then f of x is concave up on AB. Next one. If f double prime at C less than 0 on some interval AB, then f of x is concave down on AB. Finally, if f double prime of C is equal to 0, then x equals C is the inflection point. What's happening at the inflection point? Your concave down becomes concave up, or concave up becomes concave down. First example that we are going to, well, I'm going to verbally give you the first example, and that is just x squared. X squared is just a parabola. It opens up. The whole problem is concave up, right? That's it. Done. But let's take a look at x cubed. Y equals x cubed. To do the second derivative test, we need the second derivative. Your inflection points are calculated in the second derivative. So we find f prime of x, which is 3x squared, and then we find f double prime of x, which is 6x. And that's the one we are interested in. So f double prime of x equals 6x equal to 0 to calculate that x equals to 0. You see, that x equal to 0 in the second derivative is your inflection. It's the x-coordinate of the inflection point. So inflection point at 0, 0, right? When you plug in 0 in original problem, you get 0 for y. Second derivative test, I told you, same deal as first derivative test. You partition, pick the test points, and now you test in the second derivative. So here's my partition at 0. we are on negative infinity to positive infinity. We pick negative 1 and positive 1 as test points. And then f double prime at negative 1 is equal to negative 6. So we have 6 times negative 1, which is negative 6, less than 0, implies f of x is concave down. You could just put CD, concave down. F double prime at 1 is 6 times 1, which is 6, which is larger than 0. F of x is concave up. Now if you compare that to the graph of x cubed, you see your inflection point at 0, 0. Do we all see the concave down part before 0? This piece, it looks like concave down. If you complete the, right? It's a concave down. So this part of the line here is concave down. And this part of the line is concave up. Cool, huh? Whatever.
I just want to know when it's going to get hard.
I'm sorry, the lecture is over, so we go and talk about the review now. Sorry for disappointment. Maybe I can find something that has a product rule and the chain rule in the same problem, and then try to get to the second derivative after 15 lines of. Is that what your heart desires? Answer. You want those last 2 points, right? F of x is concave down on negative infinity to 0. F of x is concave up. You can spell it out if you want. On 0 to infinity. This is the answer for the problem. If you are able to take the first derivative and then the second derivative, set it equal to 0, solve equation, partitioning and everything, guys, every step was the same, right? Get all the x's, partition. If you have vertical asymptote, partition that as well, and then use the test points, calculate test points in a second derivative, and you're done.
So I'm guessing it doesn't really matter if we use the square brackets for the 0?
It does.
Oh, it does?
Because you cannot have a square bracket for a 0 on top and a 0 on the bottom, because if you use the square bracket, that means that the 0 belongs to concave down.
Oh, okay.
And then there was only one instance when I used square brackets, and that was where the problem required the closed interval on the other end. But when you are making your intervals, they all have open brackets, because you do not get to claim increase on one point. You cannot say that the function is increasing on one point. It can be increasing on the interval, because interval has multiple points, and then you can compare their y values and say, yeah, it's going up or it's going down. If you have just one point, well, you have nothing to compare it to. And the difference between square brackets and the parenthesis is exactly just one point, the end point. So you can't claim increase, decrease, concavity for the one point, which is why we always use parentheses. Unless the problem said, chop it up. There we go. See? It said 0 to 2 pi inclusive. Well, if you take a look at my calculations, they all have parentheses, because I'm excluding those points, because I can't include pi over 4 in both intervals. So that was the reason. You're welcome. You'll have the square brackets only on the ends if they provide the closed interval. Anything else? So tomorrow, after exam, we are going to graph functions by hand. That lecture is going to have shopping list of 13 different bullet points, which are different calculations, that we work on a side so we are able to graph function by hand. What kind of function? Let's say x squared ln x. Or 1 over ln squared. Something, something like that. Obviously you know which way x squared plus 3 goes, right? So something like that we don't bother with. But we definitely bother with x ln x or something crazy like that. And out of those 13 bullet points, about 4 will be covered by this lecture, 5 will be covered by this lecture. You will have to find the domain, x-intercept, y-intercept, all different asymptotes, first derivative, second derivative, first derivative test, second derivative test, right? So I listed already 10. So some of the stuff, it is very systematic, but each problem is, right, well, 20 to 40 minutes, because we have to calculate a whole page of calculations. You will have a whole bunch of points and things, and then you will put the graph together. So you will be able to graph pretty much anything by using this method here, along with some of the algebra. So we are going to do that tomorrow after exam. Now, after the break, we're going to go into review, and then if you guys need more time for the lab, since you all want to hand in the lab too by tomorrow. Now you still owe lab 3, which is also for the same exam, so try to work that one. The lab material for what we are doing right now is lab 4. So this is on lab 4. Lab 3 has your logarithmic differentiation and implicit and related rates. That's lab 3. Second half of chapter 3. So the more you do it, the more you practice, but that's what we have.